Right now we're going to do chapter 4, number 43, and we have this figure right here, and it says in the figure, a ball is launched with a velocity of magnitude 10 meters per second at an angle of 50 degrees to the horizontal. I'll try to draw that angle right there. The launch point is at the base of the ramp, and the horizontal length is 6 meters. The height is 3.6 meters. Plateau is located at the top of the ramp. Does the ball land on the ramp or does it land on the plateau? When it lands, what are the magnitude and the angle of the displacement from the launch point? So let's try to do part A first, figuring out whether it lands on the ramp or on the plateau. There's a few different ways to go about this, but the way that I'm going to choose to do it is I'm going to figure out how long does it take for our ball to get to the top of its trajectory, and then how far over are we? Because if we're further over than 6 meters long or 3.6 meters high, then maybe we're onto our plateau. But if we're less than that, then maybe we're going to hit the ramp. So first I need to figure out the time. And so I'm going to use V equals V naught plus AT. And I'm using this in the y direction because I know the initial velocity for x right here and for y right here. I already worked that out. And I know that at the very top of a projectile's motion, its velocity in the y direction is going to be 0. So I'm going to use this for the first half of our launch to figure out the time for the first half. So my Vy final is going to be 0 because we're at the top of the projectile. And my initial, I've already worked it out right here. So 10 times sine of our theta, which is 50 degrees, is 7.6604. And then plus our gravity, negative 9.8, times our time. So from here, I'm able to solve for my time. And I find out that my time to get to the top of the projectile is 0.7816 seconds. So that doesn't tell me too much yet, but it will, because I'm able to use this information and I could figure out how far I go, or I could figure out how high I go. But I would like to figure out how high I go, because if I know the very top point of my projectile, if it's higher than 3.6, then it's possible I went over onto my plateau. Not necessarily, but it's possible. But if it's lower than 3.6, then I know for sure that I never can get to that plateau. So I'm going to figure out what the height is. And to do that, I will use y equals y naught plus v naught yt plus 1/2 ay t squared. And so my final y is what I'm looking for. Initial y, we're starting right here at 0. And then plus my v initial y, so 7.6604 times this time. And of course, this is for the first half of the projectile, which is what we care about. So 0.7816 plus 1/2. And always don't forget that our gravity is in the negative direction if I've chosen up to be positive. And then times my time squared. Don't forget to square it. And what I'm going to find out here is that this y distance is 2.994 meters once it's at the very top, of projectile. And so what that tells me is that the highest that my ball is ever going to get is 2.994 meters, which is clearly less than 3.6 meters, which tells me that I will definitely land on the ramp. And so now I've done part A. Check, it's the ramp. But now we get to the trickier part. When it lands, what are the magnitude and angle of its displacement from the launch point? So if it were to have landed on the plateau, then I could have used my displacement being 3.5 direction, and I could solve for something there. But since we can't use a direct number, but we have to use a relationship between y and x. And I know that if I'm 3.6 up and 6 over, then I essentially need to use an equation to relate my y and my x. And so similar to y equals mx plus b, I will have y equals, and my slope is 3.6 over 6 times x, and then plus b, of course, that would be 0 because I've imagined my axes right at 0, 0. So y equals 0.6x. And this is an expression to relate my x to my y, because in all of my kinematic expressions, there's no other way. I'm not allowed to have x and y in the same equation, only time. And so this will allow me to pull those both together. And so there's a few different ways to start this, but I'm going to start in my x direction. And by the way, at this point, we're not going to really use this information anymore because I don't really care about the time to get to the top of the projectile. I'm going to care about the time when I hit the ramp at some point. So that is not going to be the same time as what I had up here. So I will use x equals x naught plus v naught x t plus 1/2 a t squared. And so my x distance is what we want. My x initial is 0. And then my initial x is right here, 6.4279 times my time. And again, this is a time until it hits the ramp, which we don't know that yet. But now I know that x equals 6.4 times time. I also know that y equals 0.6 times x. So if this is x and this is x, I'm going to plug this piece of information into my x right here. So I will have y equals 0.6 times 6.4279 t. So I have an expression for now y just with t. So I'm going to go on and use another equation to solve for my y now that I have it in terms of t, having used my x information. So y equals y naught plus v naught y t plus 1/2 ay t squared. So the y, again, is what we're solving for, somewhere up along this ramp, some distance there. But I have my y in these terms now. So I will plug in this y, which is 0.6 times 6.4279 t equals y naught is 0, because that's starting right there, plus v naught y, that's right here, 7.6604 times time, and this time is the same as each other, plus 1/2 negative 9.8 times time squared. And so from here, you can solve for your t. You can pause and go ahead and do that and hopefully find out that it is 0.7761 seconds. So now we were almost done, but we can solve for our distance up. And so I'm going to go back and plug it into this equation. So my x equals 6.4279 times this t, which is 0.7761. So I found out that my x distance is 4.9887 meters. My y, I can just use this simple equation here. I could have used this longer equations to solve for my y, but this seems easier. So I'll have 0.6 times this x, 4.9887. So my y equals 2.993 meters. So back to what we were looking for. We want to figure out the magnitude and angle of the displacement. So magnitude is what we're working on right now. And so I'll call that r with absolute values for the magnitude. And we're just going to use these two things. And so I have 2.993 squared plus 4.9887 squared. And we're going to find out that that magnitude is 5.82 meters. So that's the answer for part B. And then for part C, I'll go over here. The angle, we know that that's going to be exactly the angle of our ramp because we're on the ramp. And so I can say the tangent of that theta for the displacement is 3.6 over 6.0. And when I solve for my theta, I will find out that my theta equals 31.0 degrees. And now I'm done with my problem, and we have solved it.